I have a beam that actually bends. Okay, find the principal stress and its invariance. If you remember, principal stress are stresses that has no shear forces, right? Sigma 1, sigma 2, for example, 0, 0, right? Because there's no shearing effect. So principal stress is simply that. Now, what is invariance? Invariance is a certain constant, alright? If you remember, never mind, it's just some constant when you find the determinant, the I1, I2, you remember? This invariance does not change along certain transformation. So we're actually kind of keen to look at under what circumstances does principal stress and invariance affect the bending. Alright? And therefore we have a system to actually model it. Alright, these are the parameters. But how do we start? Alright, we know we have a matrix over here. We know that invariance is somehow finding a determinant. So therefore the first step is to find the matrices, one matrix. Alright, so therefore the first step to do, look at this example. I mean, let's talk about this thing. Alright, imagine I take a piece of this thing, I zoom in out. When we have a bending, if you still remember, this portion over here experience tensile. Tensile is pulling in this direction. Alright? And at the bottom, it's experiencing compressive. Right? But however, they are both at the same axis. Alright? And this axis, we can call this sigma 1, 1, if you still remember. Correct? We also know that there is also sigma 1, sigma 2, 2 lah. Okay? Now, you also know that although this thing will being pulled, right? There is also a shearing, because you see there is a somewhat a bending, a shearing, not bending, rather than a shearing. And this shearing is with regards to this thing going up, this thing going down, and this thing going in this direction, and this thing going in this direction. Alright, because in the in a stress system, it's a symmetry. Stress system is always symmetry, and therefore, in this direction, this is sigma 1, 2. In this direction is sigma 2, 2. Sigma 2, 1, sorry. And since we know that the symmetry sigma 2, 1 is equals to sigma 1, 2. Okay, so far so good. Doing now is trying to set up a matrix. And to set up a matrix, I have to model the system first. Alright, and therefore if you look at this cube experiences a tensile and a shearing. What about the top? Is there any forces? It didn't actually bend here, right? So therefore sigma 2, 2 is simply 0. So far so good. We have to visualize this system right now. We will have a shearing in this manner. However, because there is a stretching, we will have somewhat a slightly longer piece. And then if you were to actually piece out other finite element, you're actually having a bending that occur. Right, it's going to bend in this manner. Right? Ta-da! Okay. Therefore, I can set up my matrix now. Sigma 1, 1, sigma 1, 2, a symmetry, so sigma 1, 2, sigma 2, 2 is simply 0. So this is our our stress state. A matrix that describes the stress in its state. Now, what is sigma 1, 1 and sigma 1, 2? How can we find these values? This is the next step. Okay. Therefore, in order to calculate, we have to see in terms of 3D. Alright, this is the beam. Alright, this whole thing is the beam in 3D. Alright, and it's attached onto the wall. A long time, this beam would actually bend. Correct? Yes, correct. because of the force over here. Alright, the force onto this certain area, because it's perpendicular, force divided by its perpendicular area will give us a certain stress. Alright, as we say, force divided by a perpendicular area. This area is perpendicular to this force. Alright, it's not this meaning. Alright, it's not this meaning. This force over this perpendicular area is simply a certain pressure. Alright, we're not talking about that. Alright, so therefore, we are not talking about this. When we are talking about shear stress now, shear stress is a force parallel to the area. Alright, so it's force divided by its parallel area. So we will have a shear stress, or sigma 1, 2. If you still remember, sigma 1, 2 is our shear stress, right, in our matrix over here. Okay, so this is a very important understanding. So we have defined the shear stress. Now let's talk about what is this one, the tensile stress, or the compressive stress. In order to visualize this is more called abstract. Is that imagine I have a certain beam over here. If I were to apply a compressive stress, what do you see, or what can you see? It would actually bend. Right? If large enough compressive stress, it will actually bend. This bending has a certain moment. As you can see, this is in terms of our stress 1,1 axis, right? Correct? And therefore, when you deal with something that is moment, alright, and then also the thickness where it is the distance from its neutral axis, alright, this is y, alright, and it's a beam. And if it's a beam, now it is a rod, then it's just talking about some moment of area. And this may sound very familiar, which is MYI is equals to sigma. And this is how it's derived. And its family of stuff is talking about the Euler's-Bernoulli bending theorem, right? Talking about M over I and this one. Alright, this is the moment. This is the moment of inertia, this is the stress, this is the distance to the neutral axis, Young modulus, and the curvature radius, something like that. Alright, but what we are using now is simply to rearrange these two. So I'll just bring this y upwards only, if you still remember this formula. Okay, therefore we know that we can represent our tensile system, or our sigma 1,1 system, tensile or compressive, as my over I, and we can represent sigma 1, 2 as the shear stress. Alright, and therefore we can re-represent this whole matrix as, now it's already near 9 minutes, I'll just try to finish up, chop. Okay, so moment and y, alright, I'll just sub in the values or the equations. I would have, this is the moment, force times perpendicular distance, this is the second moment of area I, alright, and AC is meaning it's area cross-sectional. And by this understanding, let us just try to figure out what is the value that is required. Alright, and therefore, this is the question that is being given, while I'll just sub in each of this into this for a clearer view. Alright, this one is simply the cross-sectional area of this one. Okay, so therefore, this one, this section over here is B is equals to 4 cm. This is the breadth, I would call this. The neutral axis of this beam, it's y. And the height of this beam, alright, is 25 cm. And we can call this h. Now, as for this h, alright, I don't know whether this h for this, I mean this moment of area h, right? I don't know whether you should it's most likely this one, alright? But it may also be this one, because this length is 25 cm also. Okay, this whole length is 25 cm. Okay, as shown over here. This is 25, this height is also 25. Okay, while the cross-sectional area is 4 cm. Okay, and AC is simply the cross-sectional area, this side. Alright, which now I can define by taking B times H, that's all. Okay, so I have 0.04 times, alright, in meter, alright, 0.01 meter. So this cross-sectional area is this one, 0.01 meter. Now we have a force acting on this side, and this force is 10 ton, in other words 10,000 kg. If it's a force, then you have to multiply by a gravity. In this case, I write as 10 meter per second square. So the force in this case is 10 to the power of 6, to the power of 10.5 Newton, or I can just rewrite as 10 to the power of 6 Newton. Okay? 10 to the power of 5 Newton. We have also our neutral axis, if you still remember. Alright, this neutral axis is along this side. Okay? And we know that h is 25, and therefore this neutral axis is at this point, middle point. So it's y is equals to 25 divided by 2. Or in other words, 0.25 in meter divided by 2. Okay? And last but not least, the perpendicular distance in this case is this one, 25 cm, because the force is applying here times its perpendicular distance, which is this one, and that's it. Perpendicular distance is equals to 0.25 meter. Alright, therefore we have identified all of the variables over here. Alright, I didn't cheat your any feelings. My force is over here. Alright, my B, my H, my Y, my AC, all are here. Okay? And therefore, after subbing all these values, I will have 60, 10, 10, 0 megapascal, meaning times 10 to the power of 6 PA. Alright, which is a very large number. Alright, just in this case. Alright, because our force is pretty big already, and then still divided by a certain cross-sectional area that is somewhat very small. Okay, so therefore the stress is, as you know, is pretty much a lot. Let me paste this stress state into a somewhere cleaner area. Alright, this is the part. And if you forget, this is our question. Find the principal stress. Now we have our stress tensor now, which is all the way just now. I think you're already familiar with it already. Stress tensor. Principal stress is simply finding the determinant of it equals to 0. Okay, and therefore I'll just write out for, alright, I'll just identify sigma 1 and sigma 12 for them. Later on you'll know why. Okay, I'll just simply find their determinant. So sigma 11 minus sigma 22, we multiply, because determinant is just this thing multiplied by this thing minus away this thing times this thing. You get what I mean? So I'll just write it out and later you'll know why. Finding principal stress is not defining the determinant of this system. What the hell am I doing? It would be like this, minus the principal stress. Alright, because we want to find the principal stress over here. If you want to do that, then how do I find? If you still remember back, the principal stress somewhat like this, right? Sigma 11 minus sigma 22 minus sigma, and things like that. It's just, and then the rest as just sigma ij. Okay, I mean, you know, if you get what I mean. So the trend I actually forgot. So I should have, if I want to find principal stress, you just remember it's taking your stress tensor minus away principal stress, determinant equals to 0. Okay, please do this. After I do that, I'll have this matrix over here. So I'm just taking 60 minus sigma, I have this over here. and then this on top is just sigma 11 minus sigma. I'm just representing 60 as sigma 11, that's all. Later on you know why. Okay, so now then I can do the determinant. Okay, if I were to do that, I will have this thing over here. Right, this is in terms of if I'm dealing with the numbers 60 minus sigma and 10 and such. This one is if I were to deal with the notation. Alright, so this thing represent this one, and this one represent this one. Taking note that sigma 21 and sigma 12 are symmetry, therefore it's sigma 12 square. Alright, so I'm just simply doing the determinant, that's all. Taking 60 minus sigma times minus sigma, this is what I have over here. Or otherwise, sigma 11 minus sigma times sigma 22 minus sigma, which is over here. Okay, I'm just doing this. Later on you will know why. I'm just defining certain stuff. I decided to do with you in terms of finding this determinant. I mean in terms of solving this. So I take sigma 11 times sigma 22, sigma 11 times minus sigma. Alright, so sigma 11 times sigma 22 is this one. Minus sigma times sigma 11 is this one. Alright. And sigma times sigma 22 is simply this one, and things like that. Alright, so after which I will have this form. This one should be fine for you. Alright. Now is in terms of sorting that make things a bit complicated. Is that this is in terms of sigma, this is in terms of sigma square. So therefore I just group sigma, I just take sigma square over here as sigma square. Alright, and I'm factorizing out sigma. Alright, so I'm just actually taking out sigma now. And so when I factorize out sigma, I would have sigma 11 minus sigma 22. In other words, I'm just factorizing out them. You get what I mean? And therefore I have this. And please do not be complicated by confused by sigma and sigma 11. Sigma itself comes from the principal stress. Alright? Comes from this one. And if you take it as you're talking about eigenvalues, this is eigenvalues. Alright? For example, because if this may actually confuse you because so many sigma. This may be like this may be like that. This might be eigenvalue square. You get what I mean? So because I'm actually right in terms of sigma, this make you very confused. But it's actually the same thing of solving any determinant system. Alright, as you can see, now I have this form. Alright, and I have this form. Alright, I'll make it more nicer. I'll just resort them. Alright, I'll just sort them out like this. And I'll just sort this into this. I just rearrange only in terms of brackets. So therefore this one is I1 and this one is I2 for 2 times 2 matrix. Alright, and therefore this I1 and I2, what is this? This one is in fact our invariance. Alright, is our invariance. And therefore this formula, it's kind of important because you no need to straight away find the determinant. You can find the invariance straight away using this formula. Because if you want to find determinant and then find the roots, you're gonna go through all this long process, right? But with this equation, then you can straight away find the invariance straight away. Okay, but let's carry on with our blue color, this portion over here in terms of the numbers. Alright, because I actually do up two things, this thing and this thing, while also the orange color one. So I represent sigma 1 and 60. Never mind, I think you are kind of confused, but now let's do up this part. If I do up this part, what do I have? I would have this form over here. Alright, and this one is simply the same as this one. Okay, if this doesn't look right, I'll just rewrite this blue color one. Alright, I'll just rewrite this in over here. I'll just rewrite as 60 sigma and minus 100 equals to 0. And this is simply your I1 and this is your I2 value, your invariance. Do you see where the shortcut is coming? When you know this equation, alright, this is a shortcut equation, which is we have found in terms of 3 times 3 in the earlier case for this one. Alright, or perhaps this shouldn't be this one, but rather than it should be this one. Alright, this is 3 times 3. Alright, they are the same, but in terms of sigma 1 and things like that. So I'll not go through it in details, but hopefully you know what I mean. So in this case, we know that our I1 can straight away be calculated already. I1 is equals to minus 60, I2 is equals to minus 100, or in other words, it should be 60 and 100 also, if I were to positive them, because all negative, I can also become all positive, something like that. You get what I mean? Because if I were to multiply this whole equation by negative, alright, I will have positive, positive, positive. This one minus 0 is simply 0 still. So it's just the same thing only. Alright, and therefore this I1 and I2, this invariant, is our function in this working. I mean in the problem itself. Alright, this is the problem coming from chapter 23. Alright, this is the problem, and we're actually solving for the invariance. So if let's say this equation already, you can straight away sub in your sigma 1 1. Alright, your value has already been found. So you just sub it in, and then eventually you will get the answer over here and here. That's just straightforward. You don't need to straight away go through all these long processes. Alright? Because the long processes means that you're actually talking about these processes. You're actually going through the stigma to actually do this thing, alright, or the problem. I mean, yeah. So now we haven't finished yet. We are only solving for the invariance, and we actually show you how there are two methods of solving, and the shortcut method, which is to actually memorize this formula. And this is for the invariant part. The invariant part means that these values will not change across all transformation of the bending process. Alright, well, now we're going to solve for the principal stress, and therefore the principal stress is to solve for the roots of this one. And if I were to solve for the roots for this one, or in other words, solve for the roots for this one, what do I have? I realize I have a careless mistake. Alright, minus sigma times minus sigma is actually plus sigma square. Right, so along this path I want to do that. Okay, and therefore same as for this, minus sigma times minus sigma is in fact sigma square. Alright, so if I were to solve for the roots, therefore if I were to solve for the roots for sigma, alright, which is this value, alright, so sigma is equals to 61.62. Alright, or you can say that sigma 1 and sigma 2 is equals to minus 1.62. Okay, so this sigma 1 and sigma 2 will represent our principal stress, sigma 1 and sigma 2. Okay, and therefore if I were to write in terms of matrix, what I would have is 61.62 minus 1.62, 0, 0. And therefore this is our principal stress. And if you were to come to this book, is being derived over here in terms of megapascal. If you still remember, our matrices are in terms of megapascal. Alright, megapascal. If you want to all the way go back, it's over here, right? Megapascal. Shouldn't be this case anyway. Yeah, still this is the way to solve for a certain system. At least you get a feel of how the principal stresses and the matrices are being derived. And I shall see you and therefore this is somewhat the summary of this video, and it will be posted inside the description. And that's it. Goodbye.